Hello, everyone. Welcome to week 8 of our course on brain and behavior. This week, we're going to be covering chapter 9. This chapter is titled How Do We Sense, Perceive, and See the Visual World? And like I added in there, we're mostly talking about the visual systems today and over the course of this week's chapter. So let's go ahead and get into it. Here we have some of the main topics that we're going to be covering within this chapter, things to look forward to. Now, the clinical focus of this first part, chapter 9, part 1, is going to be about migraines in the case for blind sight. Now, migraines, these are caused by the dilation of cerebral blood vessels that occurs during an aura. An aura, for those of you who may not know, they are a really interesting phenomena. They may be auditory, tactile, or visual. They're usually resulting in an inability to move or to talk. And an aura is usually limited to one side of the visual field. Similarly, migraines are typically limited to one side of the head. But unfortunately, if left untreated, some of these migraines, they can last for hours or even days. Some people know that a migraine is going to come on because they first are experiencing this aura and then it ends up resulting into the migraine. So it's giving people like a little bit of a warning sign to prepare for what can be going on. Now, the severity of migraines can vary, as does the frequency and the duration. And it's often accompanied by these other kind of nasty symptoms like nausea, vomiting, and severe head pain. Migraine is perhaps the most common of all neurological disorders. It affects anywhere between 5 to 20% of the population at some point in their lives. Now, surgery may be performed when migraines begin to interfere with a person's life, whether that be their social life, their experiences with family, or on a job. And you can imagine if you're starting to experience these sensations of such a horrible headache that's starting to cause vomiting or nausea, it'd be really hard to conduct other parts of your life. Now, some of the potential consequences for these can include some of the migraine relief from the surgery, but it also can result in blindness in half of the visual field, or this phenomena called blind sight. Now, in blind sight, the brain knows more than the person is aware of consciously. And there's this really interesting case of an individual whose name is abbreviated to be DB. And that shows a really great example of some of the parallel streams of visual processing that takes place, where an individual's visual processing system is impaired uh, for really processing what these objects are, but the system for locating objects in space is not impaired. And so we'll be able to talk about that a little bit more as well as we go through the chapter. So let's get into the nature of sensation and perception. So the only input our brain receives from the real world is a series of action potentials that's passed along in the neurons to our various sensory pathways. Now, neuroscientists, they do not know how we perceive one set of these nerve impulses as what the world looks like, and another set as what we're hearing. It's this really tricky question. It almost becomes this philosophical question, too, of how is our brain constructing what this experience is as our reality? It's taking this input that's partly visual, partly auditory, partly tactile all together, and it's making the one sensation of this conscious life that we're going through. And it's important to note that neuroscientists, they understand how neurons can turn energy like these light waves into nerve impulses, and they've identified some of those pathways and the nerve impulses that travel to reach the brain. The real mystery that's going on here is just how is that then transformed into this phenomenal experience of the world around us. And although our perceptions and behaviors about them may differ, each of the sensory systems is organized on a similar hierarchical plane. So let's talk about those sensory receptors a little bit. Sensory receptors, they're specialized cells that transduce or they just convert the sensory energy into neural activity, kind of trying to take the energy that's out there in the world around us and translate into a language that our nervous system is able to understand and communicate with. So each sensory system's receptors are designed to respond to only one narrow energy band. For the visual system, that's going to be the light energy, which then produces chemical energy. For the auditory system, that's going to be using air pressure, which produces then this mechanical energy within our ears. For the somatosensory system, that's going to be utilizing mechanical energy, while taste and olfaction will draw upon the chemical molecules more broadly. Now, with our eyes as one of these examples, and we have a nice picture of some of the rods and cones that are up here, those photoreceptor cells. Each photoreceptor cell out of about 120 million that we have in our eyes is all pointed in a slightly different direction, and it has a unique receptive field. Now, these receptive fields, these are regions of sensory space in which a stimulus modifies a receptor's activity. So the idea behind this is essentially saying that the brain is using information from each sensory receptor's receptive field to not only identify the sensory information, but also to contrast the information from each receptor field that's being provided. And we have all of these, so the brain is being able to put together all of that information to create the experience that we have then later on. Receptive fields, they sample sensory information and they help to locate events in space because adjacent receptive fields can overlap. The contrast between their responses to events allows us to then localize some sensations. So there's the spatial dimension of sensory information that produces some cortical patterns and maps that end up forming each person's sensory reality of the world around us and kind of their understanding of what's going on outside of their body and in the world. So let's talk about some of the receptor density and sensitivity. Sensory receptors, they're not evenly distributed across the body or its organs. The density is essential for determining the sensitivity of a sensory system. So an example of this is there are more tactile receptors on the fingers than on the arm. And you'll notice that just because as you're going around and you're feeling things, if your hand or your fingers brush against a part of a page, you're able to maybe feel each of the different pages in the book with a lot more of a fine-tuned sensation compared to if you were just to put your wrist or your forearm against the same part of the book. You probably wouldn't notice the same distinction between each of the pages along the side. There's also differences in receptor density that determine unique abilities of many animals. And a good example of that is the olfactory ability of dogs, where they're able to then have a much more in-depth experience than we do. Now let's talk about the neural relays. So all receptors, they connect to the cortex through a sequence of these intervening neurons. So information is modified at various stages in the relay, allowing the sensory system to mediate different responses. And the neural system allows sensory systems to then interact. So one example of this is each of our two eyes has a separate view of the world in the visual system. If you don't believe me on that, what you can do is just stick out your arm and put your thumb up, close one eye, and then close the other. And you'll notice that if you have your thumb in between you and like a picture, your thumb sits, you'll notice you see slightly different parts of the picture, or your thumb is blocking a slightly different part based on which eye is closed, giving you just a slightly different view. Now, the information from the two views is combined in the thalamus so that then the input from both the left side or the right side of each field is superimposed to produce these two visual fields, one for the left and one for the right. Now, the next stage of the relay is that the brain separates different aspects of the visual input. That's going to be some of the more specific things about whatever you're seeing, like the shape and the color. There's a second visual pathway that also goes from the retina to the superior colliculus, and then to the thalamus and cortex. And this pathway is involved in the perception of movement. Neural relays, they also allow sensory systems to interact. One dramatic effect of sensory interaction is the visual modification of sound. So if a person hears a speech syllable, such as ba, while observing someone articulating ga, then the listener hears not the actual sound ba, but a hybrid sound of da. So viewing the movement of a person's lips actually modifies the listener's auditory perception in this really interesting way. And we're seeing that interaction of those sensory systems take place then. And this is something too, if you want to just play around, you can YouTube this phenomena, and they have some really interesting videos where it's the exact same audio that's being played, and they just have these actors or actresses mouthing the sounds ba or da or some other phonemic syllable. Now, sensory coding and representation. Sensory information is encoded by action potentials traveling along the peripheral nerves to the central nervous system. The presence of a stimulus can be encoded by an increase or a decrease in the discharge rate. Now, there's this question, how do action potentials encode various sensations, such as vision and touch? Now, the answer to this is a bit complex. Different sensations are processed in other areas of the cortex. We learn to distinguish the senses through experience, and each system has a distinct wiring set up at all levels of neural organization, which helps this experience to take place. Let's go ahead and now talk about the neocortex in the sensory fields. So the neocortex represents the sensory field of each modality as a spatially organized neural representation of the external world. So it's really this topographic map, which is a neural spatial representation of the body or the areas of the sensory world that's then perceived by a sensory organ. In mammals, each sensory system has at least one primary cortical area, and these may project onto some of these secondary areas that exist. Here we have this rather interesting looking figure as the topographical map in the sensory motor cortex. This little creature is called the homunculus, and that reflects the topographical map in the sensory motor cortex. Although this creature looks a little bit strange, what's really helpful about this is the disproportionately large areas control the body parts that we use to make the most skilled movements overall. And there's also this reflection in what we talked about previously, where we were talking about the density of some of the areas in the nerves and how it's not evenly distributed. And we can see this really closely here too, where I was talking about that example with the fingers having more tactile receptors than the arm. And that's reflected in this homunculus, where you can see the hands and the fingers, especially, these are very, very large, as there's a higher density of some of these tactile receptors compared to the forearm, which is relatively small. Similarly, for the mouth and the tongue, these, and even the ears, these are also disproportionately large, while more of the torso is smaller. Then for perception, there's two key terms to be aware of. There's sensation. Sensation is the registration of physical stimuli from the environment by the sensory organs. So that's really trying to say that there's some type of, stimuli that's existing out in the world around us, and our sensory organs are able to pick that up. Now, what's important to note here is this doesn't mean that just because a physical stimuli exists in the environment, that it is a sensation that we're experiencing. So if you're looking forward and behind you, somebody has a flashlight on and it's still in the middle of the day, you may not have any sensation of that light being behind you because your sensory organs, your eyes are facing forward and none of it's actually being registered. Whereas if it's late at night and you're looking down a road and you see somebody who has a flashlight on, then you are actually registering that stimuli being out there. Similarly, if there's a little bit of, if it's a windy day, you're going to be able to register the tactile sensation of the wind, whereas it's unlikely that there's no air movement at all when you're outside, even though sometimes it feels that way. But when you're not really experiencing any of that sensation either, just because it's below a threshold for you to actually register that by your sensory organs and receptors. Now we're going to contrast sensation with perception. Now perception, that is the subjective interpretation of these sensations by the brain. So it's this higher order experience terminology, right? Because it's the interpretation of these sensations that's taking place. So in this case, our visual experience is not always an accurate reproduction of what is out there in the world. Instead, it's a subjective construction of reality manufactured by the brain. And we have some good examples of this right here with some of these perceptual illusions. So here above with image A, this was a piece that was done by Edgar Rubin, who has this ambiguous reversible image that can be perceived in two different ways. And so if you just look at it briefly, for some people, a different image is going to pop out to them. Some of them are going to see very clearly this vase in the negative space, the white space that's here in the center. And other people, they're going to be perceiving two faces. And we can see there's the forehead, nose, lips, chin, and whatnot. And so there's, again, this higher order process of how your brain is actually perceiving the physical stimuli that's in front of you right here. Are you perceiving it as a vase or are you perceiving it as two faces? Similarly, we have this photo here with the cheetah. In this case, it's really, I think, fun and interesting too, because we have this question of each cheetah's head can be perceived as belonging to either of the cheetah's body. So do you see this head as the cheetah looking back over its shoulder, or is this cheetah looking forward while the other one is looking back? For me personally, I kind of think that it looks like this cheetah is looking backwards and this one is looking forward, but no, I don't know for sure. So there we go. That is chapter 9, part 1. Stay tuned for 9-2 coming up next.